Hello, my name is Thorsten Höffler. I'm a professor of computer science at ETH Zurich, and today I'm going to talk about high-performance scalable deep learning and its impact on scientific computing and high-performance computing in general. First, let me thank all the contributors to this work that I'm going to mention one by one, of these different papers that I'm going to mention one by one, that are partially members of my team at the Scalable Parallel Computing Lab at ETH Zurich, but partially also external collaborators in the endeavor to make scalable high-performance learning possible and actually cheaper for the wider audience. So let me start by a motivating example, by an important application that I believe actually can drive this development because it has extreme compute requirements, but also extreme promise to change the way we do things, to change the way we as humanity operate, we interact with machines, and really opening a new set of possibilities that hasn't been there before. So this model was partially or fully pushed by OpenAI, built on a on a previous architecture of transformers. It is the massive GPT-3 model. Many of you may have heard about it, and its incredible capabilities to tell stories, write novels, answer arbitrary questions, and even answer specific questions in specific contexts with a relatively high accuracy. So this model, in order to implement all these features, all these different functionalities that it actually provides, requires 175 billion parameters. One of the most massive models, learning models that we have ever trained. Furthermore, training these billions of parameters requires a very large compute budget, requires lots of compute accelerators, and the price for this ranges from anywhere between $6 to $12 million to train. So the paper describing the model is quite impressive. I have not enough time to summarize it. I really recommend it to read it. But the main message is really that we don't need to fine-tune a machine learning model to a specific task, but we can really interact with it like with other humans. Humans are multitask solvers. So I can interact with a human and ask the person to solve a certain equation for me, or just as a knowledge base, for example, what is the capital of France? So few-shot or zero-shot learners is a principle where you want to achieve something very similar to this. So you don't want to train the model for a particular task like recognizing images, but you kind of want a more generic model that you can interact with, like with any human, through natural language. And that is the key. That's why most of these models are actually natural language-based models. So I've been talking about this a while ago. This is actually quite an old achievement, so to say. There's another very interesting achievement that happened probably using large-scale compute, is the CASP 2010 challenge, where Google, together with a set of models, actually, a set of techniques that were also driven by something similar at the core than this model, so-called transformer architecture, achieved an incredible breakthrough in this CASP challenge, where the goal is to predict protein folding structures, where we can see here the green and the blue one. Well, the green one is the experimental result, and the blue one is the computational result. We can see another structure here that is relatively accurately reflected by this simulation. And what we see here on the in this view graph is actually the score that ranges up to 240 here, and the number of entries to this particular challenge. And what you can see is that AlphaFold 2, which uses these transformer networks and is very much advanced techniques, is nearly twice as good, or more than twice as good, than the next best in the field. So this just shows us how powerful artificial intelligence techniques are today if they employ large-scale compute. But that was all 2020. So we're in nearly the middle of 2021. So what happened since then? Well, this model, the BERT model, the mascot, so to say, of the transformer models, actually lives on, goes to larger and larger heights. So GPT-3 with OpenAI is actually looking or finding very exciting applications. So from role-playing games like Fable, where you can talk to the machine, to complex design tasks, this model will have a huge impact on society. Or even programming tasks, helping you to complete code, or basically writing code just based on natural language. These are all things that may become possible in the very near future in a production context. So examples have been shown, very impressive examples have been shown here. So and that is The commercialization of this model now started in around March. Of course, it's very valuable, so you have to somehow commercialize it. There's a wait list that you can join yourself if you want. The next interesting thing in this area happened just very recently, 30th of April. Like less than a week ago, this paper was updated. It appeared earlier, but it keeps updating. On a Chinese web page driven by Huawei, or open source repository, Pangu Alpha, a somewhat very similar model like GPT, but trained on a very large Chinese language corpus with more parameters, in fact 200 billion parameters. It has a slightly different structure, but it's a very, very similar goal. One of the noteworthy pieces here about this model is that the model is actually supposedly will be released open source, so at least the authors promise so in their latest draft that I'm showing here. So that would be incredibly powerful for research and humanity if these models would be completely open sourced, and everybody could use it, everybody could contribute to it, invent new ideas, and all of academia can very, very quickly move us to the next stage here. But this is just, or not just, but this is what we can do. I'm not so much an expert in what we can do with these models, but the question is, how do you get to these models? And this gets more interesting for me and high-performance computing researchers, because now many people invest in specialized hardware, so or specialized systems. Microsoft pledged $1 billion to build or support OpenAI in the previously mentioned task to achieve this holy grail of artificial intelligence that I was mentioning. For that, they constructed an AI supercomputer with more than 10,000 GPUs. And we can compute easily that this machine has about 312 teraflop per A100 instance. I mean, if this is A100, we don't know officially. And the 3 exaflop, which gives us a 3 exaflop per second total performance of this machine. So interestingly, at GTC, Jensen Huang was just announcing, also a couple of weeks back, announcing another supercomputer in Switzerland, my home country, actually at my university at ETH Zurich, of course driven by CSCS, the Swiss National Computing Center, a 20 AI exaflops machine. So low precision, but lots of power for artificial intelligence computations. So this means really that we are going into an era of more and more specialization, and the specialization is now driven not by game consoles like it was in the past, or by graphics rendering where GPUs came from. The specialization is driven by artificial intelligence architectures. So many startups are trying to build this big challenge, this human brain like digital object, or maybe not even digital object, maybe analog object, we shall see, that can really act as a machine emulating the skills of real human players. And this already turned into a multi-billion-dollar hardware industry. So pretty much all the major players, led by, of course, NVIDIA, who has a lot of, is way ahead in this game. But many other players are pushing into this game, like Google with the TPU, IBM with neuromorphic chips, Intel with the Nirvana architecture, Qualcomm, and many different startups. All of these startups have the hope that they can be driven by the wave of artificial intelligence forward to have an incredible market. And you can just see that pretty much every company, also every established company, you can see here AMD, is in this game. So everybody in the IT field is building or helping to build artificial intelligence accelerators, because that is going to be the next big move forward. So we as scientific computing researchers, or I myself, ask myself, well, how can we benefit from this movement to drive the scientific use cases of the next generation? So for example, how do we use this to either predict the weather or predict the health of the Earth in general? So predict the climate of the future and see what the human impact on the climate could be with various simulation studies. So for this, in order to understand this, we would need to first understand how we do climate simulations or also weather simulations in general. The way this is usually done is that at the initial conditions, so let's say we want to predict the weather from today, we have certain measurement values that we get from sensors. And these measurement values have a certain noise in them, a certain uncertainty. There may not be sensors everywhere in the grid. So what you do is you start multiple different simulations with slightly perturbed, with a specific input distribution, slightly perturbed values. And then as the simulation moves ahead and the forecast time goes more into the future, this spread will widen or narrow, depending on the model properties. And we are really interested in this output distribution of the model. So if you're a machine learning person, it's very similar to an information theoretical view of deep neural networks. But in fact, in this particular work that we have done, I want to highlight really what the main idea is, that we want to correct or predict two things. So one is we want to understand what the spread of the distribution is, the output distribution. So we take a limited number of ensembles of the input, not all of them, because they would be computationally too expensive. At the end, we want to save computation power with this. And then we use this limited number of ensembles and we predict the spread as if we were running more ensembles. So a relatively simple training task if you have all the data ready. A second network that we use in this particular endeavor is, and for this, by the way, for the spread prediction, we use a ResNet, for those of you who are interested in the details. A second network that we are using is a 3D UNet plus a locally connected network. And here we try to correct the bias in the data. So here the idea is not to predict the spread, that's done by the first network, but the idea here for the second network specifically is to predict what we want to compare the output of this function that the simulation implements and the actual true data distribution. Or it's not a data distribution in this case, it's the actual true observed data. Because again, we have a temperature sensor and we can now compare what the real output value is. And this way, we can actually introduce local biases. This is where the locally connected network comes in. We can introduce biases like mountains, cities, lakes, or oceans. Well, oceans are typically represented in the model, but cities and specific landmarks like trees or sharp mountains may not be represented in your simulation environment. And of course, they have an influence on the weather. So you can just learn those if you change the function slightly for each grid point. And this is what the second function does. And so I don't want to go into too much detail. You can read the paper that is referenced on the top left of the slide. But in this paper, you will find a result for the simulation of the tropical cyclone Winston, which was on February-March 2016. And the result, just roughly, it takes a while to read these diagrams, but this is the comparison between 10 ensembles and the actual measurement. And we are plotting the error at Z500. So that's just one of those predicted values. And you can see here the bluer the better, and red is not so great. So you can see the eye of the cyclone, where the prediction is not very accurate because of course it is a low resolution, well, relatively low resolution given the size of the cyclone grid. And so that's not the best prediction. What we can now do when we can now first compare when we go from 5 ensembles to 10 ensembles. So what does it help to double the computational power, to double the number of trajectories that I'm showing up here to going forward. This helps with the resolution in certain areas like these, and in the with the prediction, not the resolution, with the prediction also around the center of the cyclone. So if you now use the deep learning method, you see suddenly much more blue. And remember, the deep learning method also starts from 5 ensembles plus a deep neural network, and we compare it to the 10 ensemble run. So actually, we significantly reduce the prediction error here. In these blue areas, we slightly increase it in the red areas. So this is a first success where we can show that this technique is actually useful. It's not to be interpreted as something that we can put into production tomorrow, but it just shows that there is something to be done in this area, which makes it quite interesting for the future. So that was just one little example of how we could use this. But the bigger picture is really to develop something like a digital twin of the Earth so that we can always simulate and understand how our planet is going to react to certain policy decisions. Or we can also predict certain extreme events like hail or floods and help policymakers to circumvent these problems. So, or prepare for these problems at least. We have written an overview paper on the digital revolution in Earth system science that shall enable having a digital twin of the Earth. And what my personal take on this is actually, the question is, well, this paper discusses how many GPUs or what size of GPU supercomputer would you require in order to solve this problem or in order to have a digital twin. I would also say that we should be thinking about could we move this problem onto a deep learning accelerator? Because after all, the big hardware investments are going into this area. So shall we have a GPU supercomputer or an accelerator or an accelerated supercomputer, which is the most likely feature, like this machine that is going to show up in Switzerland very soon. So this machine, the world's fastest, according to Jensen Huang, CEO of NVIDIA, the world's fastest supercomputer for AI. Can we use that machine for climate simulations, for the digital twin? Of course we can. But we now need to understand how we combine scientific simulations with deep learning methods. So not only train BERT, not only train convolutional neural networks, but we really want to solve scientific problems. We somewhat understand how to run scientific simulations on these machines because we have many, many Gordon Bell prizes already that use scalable computers of this ilk. And there's a 40-year history in high-performance computing, going back to the first parallel computers, how to do this. But we are now at the beginning of a long history how to adopt changes in artificial intelligence to benefit scientific computing in general. So that's what I want to start with. Start that movement. And in the sense, we start it by understanding how we learn extremely large deep learning models, which will immediately benefit models like the GPT-3 series, but it will also benefit scientific computing in the long run. So let me start with that. How do we push the envelope in large-scale learning? So here we have a transformer model, the model I was mentioning earlier, underlying many, many, many of these language, pretty much all today, of these language processing tasks. So this model requires input, it needs to read data, of course, which requires high-performance input-output systems. Furthermore, it requires high-performance computation in order to implement the learning process. We learned in our research that this high-performance computation is actually mostly driven by data movement, so very similar to standard high-performance computing problems. The last in the triplet here is high-performance communication. So for high-performance communication, we really mean that we can use large machines, so tens of thousands of GPUs, like the Microsoft machine had 10,000 GPUs, probably a couple more. And the question is now, how do we run or train this model on this extremely large machine efficiently, of course? It's the same problem that we have with parallel computing. We really want to make sure that we're using these machines efficiently with the lowest possible communication overhead. For this, we need different forms of parallelism that I'm going to mention in this talk. So let me start with the first one, high performance input-output for deep learning. So one of the standard problems in deep learning today in a kind of smallish scale, but you can scale it up, is the ResNet-50 training model. So ResNet-50 training has, or ResNet-50 as a network, has a 3.8 gigaflop for inference and requires about 3 times that for training for the backpropagation pass. Furthermore, the ResNet-50 is often trained on a dataset called ImageNet, which has, in the most common configuration, 150 gigabyte of storage, contains 1.3 million images. The average size of an image is about 115 kilobyte. And the sizes of the image ranges from 508 byte to 15 megabyte. And in case you're wondering, what is the 508 byte image? Well, it's this nail. This actually is a quite low resolution nail, and it took me a while to recognize that it was a nail because I would not be sure it could also be kind of a low resolution screw. But of course, a correctly trained model would recognize this much better than I am because these models are already way above human performance, at least for these tasks. So if we now look at the MLPerf results for this particular training, for training a ResNet-50 on A100, the latest generation GPU, we get about 3,000 samples per second throughput for training. This means, given these image sizes, it's about 330 megabyte per second random access, because we randomly sample new images in the learning process, which requires at least 2 very fast SSDs per GPU, given the random access latency of read latency of GPUs. So if we have a scientific computing problem like CosmoFlow, which is a well-known different CNN, that requires 2 to 4 times that. So this really means that if we are training on thousands of GPUs, which is necessary for some of those tasks, we need to manage at least 2, but probably more like 5 or 6 times thousands of SSDs. So so somewhere between 2,000 and 5,000 SSDs. If we go to the 10,000 node system, that's going to be tens of thousands of SSDs. But of course, in scientific computing, high performance computing, we know how to manage very large file systems. So these are represented by many, many products, Lustre, BFS, BGFS, and various other file systems that are available for your favorite supercomputer or cluster. But now the question is, in deep learning, do we need those file systems actually? Well, probably yes, because what I just mentioned is that deep learning workloads randomly sample the input. Right? So as you know, I didn't explain it in this video, but you can watch another one, the deep learning overview video, where I explain that you really randomly sample from an input set. Well, what do we mean by randomly sample? And that's now an interesting question. Well, by random, we actually mean really a pseudo-random sequence with a fixed seed for pretty much all the learning problems that I have seen. And of course, a pseudo-random sequence with a fixed seed is very, very attractive because we can predict it. It still looks random to the learning algorithm. It doesn't really change the statistics. It goes basically with a random walk through the model, but we can predict the I/O pattern nearly perfectly, which we can now take our crystal ball, and we can use this to implement clairvoyant prefetching. So we understand the future. And with that, we may actually not need parallel file systems, general purpose parallel file systems. So we developed a system that is a near optimal, that we call the near optimal prefetching system, or short NoPFS, or NoPFS. And this system really enables to use this insight which was stipulated by Mark Sneer and then later put into practice by a student, Roman Böhringer, and Nikolai Dryden, a postdoc in my group, in collaboration with some others, where the idea is to implement a distributed cache where each node somewhat keeps a local cache, fully knowing about the future accesses. So again, using the crystal ball on the top. So, which is, I just give you an example here for actually ImageNet on 16 processes, and plotting here the access frequency and the number of samples. So this means that the expected access frequency is somewhere, so each sample is read about 5 or 6 times, and there are some samples that are accessed as often as 18 times during the learning process, by a single process. So this is great. So if we now sketch this up here, we can basically see this somewhat normal distribution. It's not perfectly normal, it's tilted to the right, as you can see here. And then we can just take the high frequency accesses. So this is access ordered by access frequency, low here, high here, very much like in this diagram. So we just take the top top frequently accessed or most often reused examples, and we plug them into the fastest storage we can get. The very fast storage, here in dark blue, slightly lighter blue, maybe a slower storage. In memory, in DRAM storage, maybe fast local SSDs, and maybe we have another storage tier so you can support an arbitrary number of storage tiers in that model. And then you derive this basically from the fixed access stream, which you can always pre-compute here. And this is relatively simple, and I just mentioned it here. So we have these different storage classes. So this is class 1, the fastest one, class 2, and so on. And then if you're outside those classes, you basically follow the prefetch stream here. Okay, so now that we understand what this does, let's look at some experiments. So you can find more about the implementation in this archive paper up here well, you can just access yourself, and you can understand all the details. But the results, we look at one supercomputer in Switzerland, the Pitt-Stein supercomputer, which is the predecessor of the ALPS system that I talked about earlier. It is a system that is moderately performant for deep learning workloads. It was designed before the deep learning, the large-scale deep learning really took off. So it has interesting characteristics. So somehow, if you're looking at the time per batch to train with this ImageNet 1K on ResNet 50 and the number of GPUs, the blue, the leftmost violin plot here is the PyTorch result. By the way, this is really the probability distribution if you take it upside down. So it's a violin plot. The thicker it is, the more likely you will observe batch times in that area. So you can see these are pretty thinly spread out on the PyTorch side. We tried it with PyTorch and NVIDIA's DALI framework just to see if that improves much. It doesn't on this particular system. And then the yellow, the rightmost part is our NoPFS. So let's look at the largest scale here. So we still see that at the largest scale of 256 GPUs, we are running relatively spread out, and it's quite shocking because if you look at the scale here, the batch time maximum on the scale is somewhat 6, but the maximum observed time is 52 seconds, which is 100x times, more than 100x times the smallest time. So there's a huge variation here. And what you can see for the NoPFS, you actually have nearly no variation because the maximum still fits on this plot, which is somewhere like 6.3 or so, I would guess, or maybe 6.5. So that is only a 10x variation. So we have a 10x reduction in the noise when reading data for this particular example. So we also ran this on another supercomputer, the Lassen supercomputer, which is an IBM machine with more GPUs per node. It was later designed so that we can scale higher on this particular machine and to larger numbers of GPUs, like in this case 1024. We did not run DALI on this machine. And here you can see very much the same results. Let us just focus on the largest one. Here again is very much the same distribution. So very, very thin, there's no heavy piece. And here the scale ranges from 0 to 1.75. And again, this particular model on 1,000 GPUs, so much larger than on the Pitt-Stein system, we see a 150x variation in these values. And with NoPFS or NoPFS, you see a very small variation. Here it's even smaller than on the other side. Well, it's probably also around a factor of 10x. So an order of magnitude lower, which of course, as you know, as a high-performance computing expert most likely, this really changes the runtime if you run this now in a loop. So now, if you the previous one was single iteration, so single mini batches. Well, now if you look at the overall epoch times, we see a significant reduction going from PyTorch to NoPFS. Here, it's a factor of 2.4, I believe, and on the Lassen system, it's even more, even bigger because it's a much larger allocation here of 1024 GPUs. So here it's a factor of 3 point something, if I remember right. So we can use this insight of the crystal ball to really circumvent all the problems of the parallel file system and implement our own specialized I/O for machine learning workloads. And this should generalize across many, many different machine learning tasks because they all have this same or very similar structure of this random sampling from a very large data set that can be made predictable by clairvoyant prefetching if, like it's common in this area, you use a specific seed, like a fixed seed. Okay, with that, I would like to finish kind of the first part of pushing the envelope in large-scale learning and move on to the second, high-performance computation. So what can you do to improve or accelerate high-performance computation for machine learning workloads? So here we did a specific work which we call Data Movement is All You Need. It's a little pun, many X's all you need papers in that field. And it's specifically a case study aimed at transformer networks like the ones I mentioned at the beginning, the GPT-3 network. So here we have a BERT encoder. I mentioned that this BERT is somewhat kind of one of the default building blocks, or establishes one of the default building blocks for this area. And we take this relatively complex structure, as you can see here. I don't want to explain all the details of it, but a relatively complex computational structure, and we try to accelerate it as fast as possible on today's NVIDIA GPUs, because it is worth it. Obviously, people are spending millions of dollars, and this is just a single experiment. Like a single experiment costs millions of dollars to run this particular model. So getting even a 5% benefit is going to save hundreds of thousands or millions in the long run. So now if you analyze this model, what is quite interesting about this is that you have three basic operator types. So three basic computations that you have to perform in order to execute the model on the GPU. So one of those we summarize as tensor contractions. There are many, many different shapes of those. So tensor contractions can be expressed as matrix multiplications, many, many, many different sizes. The second shape is somewhat statistical normalizations like softmax or some kind of other statistics function. So it's most prominent here is softmax. And the last one is element-wise computations, where it's very simple. You just sum things element-wise. So the first we observe is that GPUs have been tuned for tensor contractions. So this is the workload for GPUs. This is where they excel. This is where tensor cores are built for. This is what works. This is what has been getting faster in the last years in every single iteration. And of course, yes, it's 99.8% of the flops of the model. Great, so I'm accelerating 99.8%. Even given Amdahl's law, that's wonderful. Turns out though, it's only 61% of the runtime. And this is what we mean by data movement is all you need. because the acceleration of these tensor contraction units with specialized hardware has led to a new bottleneck, which is now data movement. If you have 40% of your time spending moving data around, so not in these highly optimized units, well, then your speed up is going to be very limited by further optimization of these units. So now we need to focus on how to move data through this machine. And here we specifically see that 0.2% of the flops cause these 39%, nearly 40% of the runtime, because these models have been optimized very much for tensor contractions. So what we show that we can actually use the same architecture just by optimizing the data movement, optimizing data layouts, and achieve a significant speed up over PyTorch, TensorFlow, and also a hand-optimized version for that architecture on this for that network architecture on this particular target GPU, which is Microsoft's DeepSpeed. And this, of course, if we now do the math, we can save $3.6 million just for the single GPT-3 model, or $85,000 if you train BERT on an Amazon machine. So relatively big savings, and of course making it 30% faster is a big deal in this area, and also in high performance computing in general. So how did we do this? Again, I can't explain the whole paper in detail. You can read it at this archive link, but I can give you a little bit of an overview that you understand the gist, what is going on. So we first expressed this overall problem that you've seen on the previous slide as operators with data flow. So we express it as a data flow graph, and here it's an annotated data flow graph, also too complicated to explain all the details. Again, please review the paper. But here we annotate, for example, the number of floating point operations and the operational intensity. So, and here are the input matrices and so on. And then from this graph, by the way, this graph can be designed with the help of our programming framework, DACE, Data-Centric Python, which you can find at the URL. It is more or less able with still manual help to do these things today. In the near future, it will be able to do many of these things fully automatically. So we are very much working on this. This is still a manual experiment, but we are working on fully automating that process. So first of all, what we do is for each of those tensor contractions that you can see here in Einstein notations, we try different data layouts. You can see that the spread, and again, this is a violin plot, shows you the likelihood that you achieve for a certain experiment. This is one particular matrix, or not matrix, tensor contraction, for one experiment with different layouts. So here we transpose the two matrices in different shapes, and there are a lot of different combinations. Here you can see the probability distribution of, if you draw a random shape, what your performance will be. Furthermore, we investigate different fusion strategies, because some of these operators you want to fuse together in order to cut the data flow inside the loop. Right? And here we can see also a relatively huge spread where we have, for this particular example, where the best fusion strategy for these tensors here, or these operators, is 0.033 seconds, and the worst one is 0.86. So again, nearly a factor, or more than a factor of 20 in this particular case. By the way, the really bad ones are unlikely to be chosen by any intelligent human. So the intelligent human chooses relatively good, so the DeepSpeed team, for example, was basically chosen by you, who choose relatively good configurations. But what the problem is for an intelligent human is that the configuration space of the overall model is very, very large. So that's what I'm showing here. So that is the configuration selection graph of the overall model, where you basically have these vertices in this graph, these vertices on this graph are specific data layout. Here, for example, BJI versus IJB for a specific tensor. And these boxes we are drawing are specific fusion strategies. And now you can combine the different layouts and the different fusion strategies in an overall selection strategy, and then apply a search algorithm in that space that we are establishing here to find the best configuration. Right now we do this with a lot of compute, so we do a lot of manual experimentation to get these probability distributions and then design this configuration space. But tomorrow you may be able to do this with reinforcement learning or anything more intelligent. And with that we achieve currently the fastest result for implementing BERT or many other deep neural networks on a specific GPU architecture. Of course, that needs to be needs to be retuned to different architectures, but so far it generalizes pretty well to similar architectures. But the workflow is always the same. So you can use that workflow to achieve high performance computation in this deep learning context. So that will get me to the last part, high performance communication in deep learning. So how do we really implement high performance, very large training systems on very large machines? Because we want to use tens of thousands of GPUs. We want to use all kinds of different parallelism schemes. So with that, I want to first summarize the 3 dimensions of parallelism in deep learning. So again, here there is an archive paper where you can go into arbitrary detail. This is in fact a very comprehensive survey paper written by my postdoc senior scientist Tal Ben-Noon, who's working on this, who has been working on this in the past and is now moved on to understand what are the axes of parallelism in this model. So let me first introduce the learning in general, where we have usually trained on multiple mini batches. So there's mini batch 1, mini batch 2, mini batch 3, mini batch 4, for statistical reasons, to accelerate the learning process. We could always go through all batches, through the whole batch, to all the data, but that would make the computational overhead too high. So we subsample a random mini batch from the large data set we have, and then we train multiple iterations. This is through these different mini batches, 1, 2, 3, and 4 in this case. So now, if you want to parallelize a model, the simplest possible way is data parallelism. So with data parallelism, what we do is we take a subset of a mini batch and run it through a model, a full copy of the model. That's the green model here in this case, up here. So then we take another one in parallel from this mini batch, because we drew the whole mini batch before, and run it through this bluish model. A completely separate copy of the model on a different GPU or different sets of GPUs. And then we take another one, in this case a third one, and run it through this reddish model. So after we've done this, we need to, of course, synchronize the models, and I will be talking about that in a couple of minutes. But this is the simplest possible training. We just replicate the model. Of course, if the model is too big to fit on a single GPU, which most large-scale models are, there's not enough memory in a single GPU to even hold it, then what we need to do is we need to actually distribute the model. So there are now 2 different ways to distribute the model. The first way is so-called pipeline parallelism, which is a very useful way, because the communication volume you have to perform in order to keep the model correct is most likely smallest for many configurations. It depends on the operator, but for most of these models, this is very beneficial. So what you do here is you run your first operator, like this larger convolution object there, you run this on accelerator 1 or on node 1. Then you run the second operator on a different node. So of course you have to now communicate for each of those between the yellow and the reddish background accelerator. And then the last layer, in this case a fully connected layer, you run on the third accelerator. So now you see where the word pipeline comes from, because each data object moves into the first accelerator, then into the second accelerator, then into the third accelerator, while the first accelerator is already processing the next or the next after the next example. So it's really a pipeline, like in the traditional computer architecture or manufacturing chain. So then the last form of parallelism, the third dimension in these models, you can parallelize a single operator. Like in this particular case, this fully connected network, you can take the 6 input neurons, and it has also 6 output neurons, and you can put pairs of neurons, so 2 neurons each, on different accelerators. So here again, the blue, the red, and the green one. And you can do this for each. And now you can combine data, pipeline, and operator parallelism into your optimal model configuration, your optimal parallelism configuration, which is a very, very interesting topic. So again, if you want to learn more about this, look at the paper on the top. Many follow-up papers have been designed for now cutting these models, how to adjust data, pipeline, and operator parallelism. So this is a very interesting field. Okay, but now let's look a little bit more into the data parallelism, because as I mentioned, that is the default parallelism scheme. It is also still considered the simplest and the most valuable to some extent. What you need to do there at the end of each iteration is you need to sum up the gradient values. Right, so across each of the models, you have now different gradient values coming in the back propagation step. You now need to sum them up across the model. The question is now, well, why do you need to sum all of them? Because it's a statistical process anyway. Yes, what you can do, in fact, is most of those gradient values can be skipped and locally accumulated, and only accumulated every kth iteration. So you don't need these at every single iteration. So here in this particular work, the top K SGD that we did with a collaborator, or actually Dan Alistar proved all these things himself, and we just helped him with the implementation. We're basically implementing this top K idea where we take a very small fraction of the gradients at each process and then move it to reduce it across these processes. So really 10% or less of the gradients need to be sent. And you can prove this all mathematically. I don't want to go too much into details. It's a very nice proof that I highly recommend looking at if you're interested in this field. You can show it empirically, or you can show that the assumptions for the proof are correct empirically, and then you can show empirically that this actually works for real training examples. So let me go a little bit more into detail on the systems contribution. This is now another paper where we describe how we implement this on a real system, because it's also very interesting. If now every processor chooses a random subset, a pretty much random subset, but a small one, like 10% or less of the gradients, what you will have is you will have different gradient distributions across these different index sets across these different processes. And as you sum them up in this all-reduced style algorithm, where first each of these neighbors communicate, and then the neighbors of the neighbors communicate, the network gets denser and denser, like in this example. And at the end, of course, it's somewhat in the densest configuration. It's a very unlikely that two non-zero values sum up to a zero value, but it's basically extremely likely, or likelihood is one, that a non-zero value plus a zero value is always going to be a non-zero value. So the network's going, the gradients are going to densen up. And in this particular work, what we do is we play all kinds of tricks to optimize the algorithms to start in a very dense representation, and then in the middle somewhere switch, very sparse representation, and then in the middle somewhere switch to a much denser representation. And we achieve really remarkable results on a Microsoft Speech production workload. These were still RNNs at the time, where we were able to accelerate this from 2 weeks to 2 days given this technique. And there are many, many other results on the Pitstein supercomputer, also on EC2, where the speedups were much higher, because on a supercomputer, the network is already very good to begin with. So we get a speedup of somewhere between 1, 1.3, and 4 maybe. On the Amazon cloud, on a normal Ethernet network, we get much higher speedups because the network is simply not high performance. And that was before the times of the high performance network introduction in Amazon, before the Nitro NIC. Okay, so now we just learned that the gradients are mostly sparse, or can be mostly sparsified. But there is another interesting effect. When I talked about the ImageNet example, I told you that the images are ranging somewhere between 500 byte and 15 megabytes. So there's a very large imbalance when reading the images. It's not so prominent there, but there are other examples. In reality, it doesn't matter that much because it's kind of averaged out. But there are other examples, like the UCF video data set, where the number of frames per video, so the length of the video, so to say, is very unbalanced, ranging between a very small number up to 1800. Right, or 1776. And this with a very high standard deviation somehow, because the mean is 187. This results in a very different runtime of the LSTM, because an LSTM runs across all these frames on the P100 GPU. So here again, the mean is somewhat 1.2 seconds, and the standard deviation is 700 milliseconds, so a very, very large standard deviation, because the distribution of the input videos is so large. It's pretty obvious. So now, if we would train this in the synchronous SGD setting, what we would do is we would do the compute, and now each process would take a different time. So some process would be very fast, like this one, and like other processes would be very slow. So then these processes would all wait for the last one in this case. So only one process would not wait. Then we would perform the all reduce. Then we would do the next computation. And again, there would be slow and fast processes. The slow processes would need to wait, the fast processes would need to wait for the slow ones. We would perform the SGD, or the all reduce. And again, we run into the next iteration, where we have again slow processes and fast processes. The fast ones have to wait for the slow ones, and you can see where this is going. So at the end, most of the time, most processes are somewhat waiting, because they're really waiting for the last laggard process. So in our eager SGD idea, which was developed by Shigang Li, a postdoc in my group, this eager SGD, we still, of course, have the same computational imbalance. So we still have the slow and the fast processes. But the idea here is going back to a very old idea that Salvatore Di Girolamo had in my group, where we are going back to a solo collective. So we can actually run a collective operation without all processes participating. In fact, we can run it with only one process participating out of the P processes. And the operation itself would progress independently through the network and through all these other processes and just grab the data that is available at the moment. So it may grab the data from this very slow process, these gradients, that are not even readily computed. So the question is, can this be successful? Yes, it can, because what you can also do is you can adjust this, that on average, you will only fire the asynchronous collective or the solo collective if more than half of the processes arrived. So this is what we are showing here. So on average, if half of the processes arrived, like this, this, and this, and even a little bit more than half, then, oh no, actually, no, sorry, it's this and this. Then you will just fire the collective, and then of course, after this collective is finished, the processes that were already finished will continue with the next iteration, and the processes that are still in the old iteration will finish that iteration before they continue with the next iteration. And you can see you now have somewhat of a natural overlap that introduces this natural load balancing feature here, because now the statistical distribution across the multiple iterations is not going to amplify itself. So you can also think about this as a relation to the operating system noise paper, one of the best papers at supercomputing, or actually the best paper in 2013 that I wrote myself, trying to understand what the impact of different distributions in a bulk synchronous application is. Here, we turn a bulk synchronous application on the top here into some relatively asynchronous application at the bottom. We can ignore half of the processes suddenly. So it's like semi-bulk synchronous. It still has features of the bulk synchronous, of course, but it's not exactly the same. And now you can implement this all on the NIC, on a smart NIC, or in a hardware thread running on the CPU, accelerating these asynchronous collectives, these solo collectives, I have to be precise here. And here you could also use a work that's developed in our lab, the SPIN work, which is really a general purpose programmable smart NICs. Okay, so now we can take this one step, well, now let's look at the results, what this gives us in practice. So we actually trained an LSTM on this UCF 101 data set and task using 8 GPUs. And you can see that here the eager SGD is significantly faster, getting to the same accuracy as the synchronous SGD using Horvath in this particular case. And just to summarize the results, so if we take the example where the first arriving process triggers, which leads to a lower average top one test accuracy. So if we can accept a lower accuracy, we can actually get a much higher speed up, so 1.6. But this is red because it changes the statistics significantly, while if we change the statistics or the learning process less, we're still changing it, it's not exactly the same, where the majority triggers, so we have a better gradient, so to say, a better approximation of the true gradient, then we achieve pretty much the same quality as the synchronous model at a nearly 30% speed up for this particular application. So that is something for unbalanced training workloads. Right? For balanced ones, it doesn't help that much, but for unbalanced ones, it gets rid of the imbalance. Now we can think about the next step. Actually, what you can do in machine learning is even more fascinating. You don't have to necessarily sum the gradients. You can also apply the gradients locally, and you can sum the resulting models. So this is called model averaging. And the idea here is that we can delay the summation even more, because now we are somewhat asynchronously learning locally, but then communicating globally to every now and then learn about what the other processes have learned or their weights. And we can go further and say, well, not all processes always need to communicate, so I can communicate on subsets of processes and exchange those weights to increase my, my learning effect and still have low costs. And this is what WAGMA SGD is about, also developed by Shigang and partners together all with Dan Alistar. So the idea is still very much the same, so we have the same distribution here of arriving processes, but now, instead of all processes exchanging data, only every odd process exchanges data. The first, the third, and the fifth. And then they move on. All of the processes apply the gradients locally, but here it's just model averaging, essentially averaging the local copy of the model. Then they run into the next. And in the next iteration, the even processes exchange the data. Or if you have an all reduce with log n stages, it could be log n different groups of processes performing this. And then you move on, and every now and then, every n iterations, okay, this n should be not overused here, this should be log p maybe, and every couple of iterations, we do a fully synchronous model update. So this turns out to be extremely efficient for deep learning or deep reinforcement learning workloads. Like we tested the proximal policy optimization in the habitat environment, And here let's just look at 1,000 nodes. Here the idea is that the higher the bar here, the more throughput, the more experience steps, the more learning steps the learner can do. And reinforcement learning has this interesting open-ended learning task. So you can just learn more and more and more and more. You will probably never exhaust the search space of your possible configurations because they're usually extremely large. So here we can see that WOGMA SGD is the second fastest, so the second highest throughput, with nearly a gap of 2 to the third and fourth one. And there is this ADP SGD, which is kind of the fastest one because they nearly never synchronize, they very rarely synchronize. So you can see that actually in the achieved accuracy, where ADP SGD is here the yellow line very much at the bottom. So the accuracy here is the SPL score. The higher the better. And here, unfortunately, the yellow very, very fast ADP SGD doesn't actually learn much, while the WOGMA SGD goes very quickly, and this is now the training time in hours here on the x-axis, goes very quickly above the standard SGP approach in this case, and beats, so to say, in the accuracy for the same compute power. And this is, of course, great, because now you're investing a certain compute budget and you get better accuracy. And you couldn't care less if that is synchronous or not, the whole learning process, because after all, our brain is not synchronous. But okay, our brain also doesn't have multiple model copies, so it's probably not the best explanation. But really, the effects show in the results. So now, let me finish this part and just give you a little bit of an overview. How do we now know how to train high-performance I/O, high-performance compute, and high-performance communication. We employ those to train large-scale neural networks. But now the question is, how do we now train models that are larger than what the largest computer can even store? Right? So I'm getting very greedy now. So I'm saying, okay, well, the GPT-3 model may still fit on my 10,000 GPUs, but now I want to train models that are much larger than this. Is that possible? Yes, it is possible. Because we can now, or we could train sparse models. We could say, well, these models live in an incredibly high-dimensional space, like in scientific computing. And we could then just say, well, but not all values are non-zero. Not all values matter. And today, all these models are dense. Well, most of these, a vast majority of these models are dense in the sense that they're fully connected. Like this layer here is fully connected to this layer, and we have all of these weights that need to be applied. So it's a full dense matrix multiplication. But actually, not all features are always relevant. You can think about this yourself. Train your brain. Read this sentence. It is sparse. Some features are removed. I'm pretty sure you can still recover it. And that leads to often less overfitting, more interpretability, at least for smallish networks. And of course, the parsimony we are after, that we can train much larger models than we could otherwise fit. But now we need to train fully sparse, which is very, very hard. So in other words, what we are doing is we are either removing some neurons and all the adjacent connections, or we are simply removing some of those connections. These are different ways to do this. Sparsity is a very, very complex topic. Some of the key results is that we can sparsify a ResNet 52 down to 95%, so 20x potential savings at about the same quality, essentially the same quality. So this is, as I mentioned, a very complex field. I've spent nearly half a year reading more than 400 papers, and I wrote an overview of that field, which is about 90 pages, together with numerous co-authors here that graciously supported me with this, on sparsity in deep learning. And the idea is really, well, how do we utilize that concept of sparsity? Or how have people utilized it at the past? And then some ideas how to utilize it in the future. So one of those is training extremely high-dimensional sparse models, but it's just one of those. It's one subsection, but it's very relevant for the purpose of this talk, because high dimensionality captures a lot of information, which is somewhat the opposite of the curse of dimensionality. Because the curse of dimensionality tells you a very high-dimensional space is very hard to navigate because it contains so much potential information. Right? And we now exploit the opposite. A high-dimensional space can contain a lot of information, so meaning it is very, very powerful. And in other words, full models just do not fit the machine. And in this paper that I mentioned, section 243, with more than 25 existing papers, explores this line of thinking to have very large trained models trained in a sparse environment. And there we can look at dynamic sparsity, where we have to iteratively prune and grow neurons or weights during training. Nest is one example where you really go through a stage from the birth brain, like in humans, where the brain typically has less connections when it's initialized. Then it grows to a relatively dense structure, the baby brain, And then it shrinks again in the towards adulthood, which is unfortunate, but that was observed. Then there are other methods to do this that are not naturally nature-inspired. So one of those is the set model, where you maintain a balanced configuration, where you combine and pruning during regrowth and training. And then another model is static sparsity, where you just fix the sparsity structure up front when you just before training, and then you don't change the sparsity structure. There are many ways to do this. So you can do it randomly, you can pre-train data dependent, or you can just design things. After all, CNNs, convolutional neural networks, are sparse structures that are just handmade for a particular purpose with a very strong locality bias or locality prior. Okay, now the question is, let me close my talk by a little bit of an outlook on the impact on high-performance computing that I already alluded to. So somehow, I believe deep learning will shift high-performance computing big times, very much or even stronger than what GPUs have done till today, which came from a different market. They came from the gaming rendering market. They pushed into high-performance computing. They changed the field as we know it today. It's nearly unthinkable to have the top 500 list without GPU systems. Complete change. And now, like 15 years ago, when we were thinking about how can we use these GPU architectures, and there were some pioneers making very big steps to bet on this with a very large system, like the Pitt-Stein system, in fact, in Europe. The first very large-scale GPU system, being number one for a long time, thanks to Thomas Schultes, who's the director of the Swiss National Supercomputing Center, making this very bold step forward. Now the question is, we need to understand and think about how hardware accelerators designed for machine learning, not for gaming, can be used to make this big step. We need somebody to make this bold step. And it may be Thomas again, because the large-scale machine, the Alps machine, is one of those very much in this category. Furthermore, I would go as far as even the ones that tried to resist. There were many of my friends, I'm unfortunately getting older, who tried to resist that movement, who said, oh, GPUs will die away. They had no chance but follow. All of them today, well, not all of them, but 95% of them today are computing on GPUs. Right? They just came late to the game, and they lost the time, they lost the advantage. In fact, one interesting story is that the Summit system, it was designed with GPUs, but they got tensor cores without even asking for it. They got them for free. They kind of learned after they signed the contract, oh, by the way, you will get tensor cores for free. See what you can do with them. That's exactly what I'm talking about. These machines will be the future. Tensor cores are designed for deep learning. They're not too useful for scientific computing. We show this in an SC19 Gordon Bell winner, where we try to use these tensor cores, but in fact, they only give you a very little benefit. But maybe there are algorithms that can exploit them. Today, we don't know these algorithms, or maybe we do, and I don't know of them. Please let me know in case you have them. But really, we want to understand how to use those. And now let me give you some challenges, because it's all about the algorithms and software. The hardware is clear. We understand the hardware. We know how to build deep learning accelerators. We know how to build deep learning networks. The real action is software and algorithms. So we have I identified these following 4 challenges. So one is we need to understand how to use low and mixed precision data types, like the FP16 I mentioned, or B-float, or other data types that may be showing up. Furthermore, we need to understand how to integrate learning in the simulation pipeline, because after all, we want to accelerate simulations through deep learning. And the next generation will have tensor units, sparse tensor units. We already have tensor units today, but the next generation will have sparse. In fact, the A100 already has sparse tensor units. Well, it's only 50% sparse, but there may be coming more. And at the end, we need to understand how we unify sparsity in learning and scientific simulation, because they have very different structures today. And it would be very interesting to unify the two if we can use those together. So with that, I would like to finish my presentation, and please let me know if you have any comments.